Hi, it's Kate, and this is the first video for week 5 of Math 23B. So last week we discussed the need to use other types of coordinate systems to describe space or the plane. We learned the 3 key pieces to setting up an integral in the parameter space. The first one is knowing your parameter bounds, figuring those out. The second one is putting your function in terms of the parameterization, composing it with your parameterization. And then the last one is making sure to multiply everything that you're integrating by the absolute value of the determinant of the Jacobian of the parameterization. Now, that's the volume stretching or scaling factor. This week, we're going to talk about specific calculations that we really care about. How do we compute volume? How do we compute area? Things of that nature using these particular skills that we've been given. So let's get started. Let's start in the plane. We're looking at R2. We look at the line segment from A to B along the x-axis. It has a 2-dimensional volume of 0. Obviously, it's actually just a 1-dimensional subspace. But what that really means is that if we took some 2-dimensional dyadic squares and lay them on top of a line, we could make those dyadic squares as small as we like and still capture the line. So that means that you can take a set of dyadic squares whose combined volume is less than any epsilon greater than 0. Note that a line, though, still has 1-dimensional volume. It's defined in terms of 1-dimensional dyadic cubes, and 1-dimensional cubes are just tiny intervals. Similarly, when we move into R3, if we look at a rectangle in the xy plane, it has a 3-dimensional volume of 0, right? It's a flat object. If you wanted to find its volume, you'd be like length times width times height, but it has no height. Note that the technical, more rigorous definition of this is saying that it can be enclosed in a set of dyadic cubes, because those are the units for which we compute 3-dimensional volume. It can be enclosed in a set of dyadic cubes whose combined volume is less than any epsilon, right? We can take these 3-dimensional cubes and capture that flat 2-dimensional object in a lot of them, but we can make those cubes as small as we like. Note that it still has its usual 2-dimensional volume, because when we take those 2-dimensional dyadic cubes, we can define its volume as length times width, which was one of your proofs from a couple weeks ago. And so our focus is exactly how do we compute these things, right? We've been looking at pretty straightforward computations so far, finding volume in R3. Note that the dimensions of what we're trying to compute, the dimensions of those dyadic cubes, that would be a 3-dimensional dyadic cube. That's a unit of volume. It matches the dimension of the space. Similarly, finding area of a region in the plane, right? Area, using 2-dimensional dyadic cubes there, that's the same dimension as the dimension of the space. But of course, there are some exercises where we're looking at perhaps a curve in the plane. That's a 1-dimensional notion of length. It doesn't have 2-dimensional area, but it's living in a higher dimensional space. Or perhaps you're looking at a sphere and you want to know its surface area, right? Surface area is a sort of a 2-dimensional notion. It's measured using dyadic cubes and parallelograms we'll talk about, but note that it's a different dimension from the dimension of the space, which is R3. So we're looking at how we make conclusions about those relationships. Note that if we apply a linear transformation t to the standard basis vector e1 in R, that's just the number 1, we know the length of the resulting vector. It's the length of the one and only column of the matrix T. And we can actually compute this length by, yes, I know that you'll say, oh, we take the square root of the sum of the squares. And I'll say, yes, that's true, but a much more generalizable way of saying that, as in generalizable as in I can apply this approach to higher dimensional examples, is by saying we can take the square root of the determinant of t transpose times t. Note that that is the same thing as the square root of the sum of the squares in this particular case. Let's take a look at how this formula, the way of writing that out, can be applied in higher dimensional cases. If we take a linear transformation t, which goes from R2 to Rn, It's able to act on the two standard basis vectors in R2 and map them to something in Rn. That means we can apply it to the unit square, and we know that the area of the resulting parallelogram, which is in Rn, is the absolute value of the determinant of t, and that the absolute value of the determinant of t can also be written as the square root of determinant t transpose t. Note that the same formula works in R3. If we apply a linear transformation t to the unit cube, the resulting parallelepiped, whatever we've mapped the unit cube into, is going to have volume of the absolute value of the determinant of t, which is square root of determinant t transpose t. So we can find length using this in a one-dimensional case. We can find area using this in a two-dimensional case. We can find volume applying this to a three-dimensional case. Now, of course, if we look a little bit more closely at this R2 example, and we say, okay, let's take a look at a specific t. It goes from R2 to R3, not just Rn anymore. That means that it's going to take the unit square in R2 and map it into a parallelogram that lives in R3. And we know that we can take a look at this matrix T and know exactly what it does to each standard basis vector by looking at the columns of T. The first column will tell us what it does to the first standard basis vector. The second column will tell us what it does to the second standard basis vector. And together, taken together, those columns span the parallelogram that the unit square gets mapped into. Now, we know two different ways to compute the volume or area. Two-dimensional volume is what I'm saying. Two-dimensional volume of a parallelogram. One, we just talked about above. We could say square root of determinant t transpose t. But the other we know from back in September when we studied linear algebra. We know that if we have T1 and T2 and together they span a parallelogram, the way to compute the area of the parallelogram is to take the length of the cross product of those. And in fact, showing that these two approaches give you the same thing, that you could find what the unit square is mapped into and the area of that parallelogram is either computed by finding the magnitude of the cross product of T1 and T2 or computing the square root of determinant t transpose t, that is going to be your first proof. That's actually only part of your proof 18.1. The other part is to show that computing area of this parallelogram in R2 is equal to the absolute value of the determinant. You'll encounter it right off the bat almost in the course notes for this week. So let's put this into a generalized context. Say we have a k-dimensional generalized parallelogram. It lives in Rn. We can look at that k-dimensional generalized parallelogram, and really we can express that parallelogram as the result that we'd get if we took the unit cube and had some linear transformation act on it. That means that we would take the k vectors that span that parallelogram, construct some t where each of those k vectors are a column of t, and it would look something like this, right? I took each of the vectors that spans the parallelogram and I made it into this matrix where each of them is one of the columns of the matrix. Now there are k of them, so this has k columns, and since each of them are vectors that are in Rn, this has n rows, which is how it maps from Rk to Rn. If we're then looking to define the k-dimensional volume of this k parallelogram, we can compute it by taking the determinant of t transpose t, as in the transpose of this matrix multiplied by the original matrix. This definition, and we take the square root of that determinant. This definition is consistent with every special case where we know the answer from elementary geometry. You're going to take a look at that a little more closely right at the start of Tuesday's lecture. But note that just brass tacks speaking, when we're calculating the square matrix T transpose T, that means that each entry results from multiplying a row of T transpose by a column of T, which is the same operation as taking a dot product of two columns of T. So for instance, the first row of T transpose is the first column of T. So you'll see that up here, when we multiply them together, what we actually have is the dot product between that first row's vector, T1, and that first column, T1. So it's actually the length of T1 squared. And then you'll see that in each of these we have dot products between T1, T2, T1, T3, T2, T1, T3, T1. And along the diagonal, we have the squares of the length. So the product ends up looking like this. It's a function of lengths and angles of the various vectors that have made up the columns of T. You might already be wondering, where does T even come from? Why do I care? This is very confusing. All right, let's take a look at our next topic. Here we are, parameterization, another application of it. Now, as we left off in the previous section, we were sort of saying, okay, I agree that the square root of the determinant of T transpose T gives me the volume of the parallelogram, the K parallelogram, that T's columns span, and that's great, I guess, but like, why do I care? What do I use this for? We're going to use this along with our parameterization skills in order to compute all different kinds of volumes, two-dimensional volume, three-dimensional volume, one-dimensional volume of different types of manifolds. Remember, smooth curves and surfaces, maybe like a helix or a circle or a sphere or a hemisphere or a cone or anything you can think of, really. So that's our jumping off point. So what's interesting is that when we're looking just as a curve, normal curve, we can look at that as a union of really short line segments. And you want to think to yourself in your mind that those short line segments are just one parallelograms, right? You can also think of a surface as a union of small two parallelograms. And I try to encourage students, I don't know if any of you are fans of older, I hate even using that adjective, but older video games. When I'm not going to say how old because it ages me, but when video game systems went from something like Super Nintendo to N64, the 64-bit gaming systems were a very big deal at one point because they were able to render a three-dimensional world. And I used to think, wow, the graphics are so cool. But then you sort of go back there and you see things as far as maybe Mario's hat or a mushroom that he's about to encounter, or even a pipe. And these things are supposed to be round, smooth surfaces, like they're cylindrical. They're supposed to be, or spherical. They're just supposed to be nice and curved and smooth. But in fact, they're made out of polygons. They're made out of these flat faces. So really what you're doing here is exactly that. You're thinking of a surface as a union of really teeny tiny two parallelograms, like two-dimensional parallelograms that have joined forces to make this nice surface. So let's think about it this way. Suppose we parameterize this curve or surface or other smooth manifold by a function called gamma. And this gamma is going to be our parameterization. Now locally, each of these K parallelograms is well approximated by applying the derivative of the parameterization function to a dyadic cube. So the appropriate volume stretching factor in this case is going to be determinant of d gamma transpose d gamma. Because those K parallelograms that we were just talking about that were so important in part 1 of this discussion, they are represented by d gamma. Now you might not even believe me, but let's think about just like a simple example of a circle. Parameterize a circle, right? Cosine t, sine t, circle of radius 1. Now, what does this look like? Well, it carves out the unit circle in the plane. When we look at this type of curve, the types of one parallelograms that we want to think about approximating this curve are ones that look kind of like this. Short little line segments. They're laid end to end, but if I had drawn them end to end, you would have been like, why is there just a red line over the blue line? So I kind of had to separate them out. And note that what's interesting is that it's not gamma that actually gives these particular red line segments or their direction, because for any value of t, gamma actually gives a position vector from the origin out to the point on the circle. So if you had a particular value for t, like pi over 2, you would actually get this vector right here. For pi, you'd get this vector right here. Those aren't giving you the directions of the little line segments. What the line segments are actually doing is coming from d gamma, which are the derivatives of this vector valued function. Let's take a look at what d gamma would be. Sorry, it got a little crowded up there, but d gamma gives you negative sine t, cosine t, and in fact, those are the vectors that are pointing along here, like so, just tangent to the circle, just like you want your one parallelograms to. And so when we're looking for, what is the circumference of this circle, that's one-dimensional volume or length. And so what you want to do is you want to describe the circle using a parameterization. And then once you've used that parameterization, in order to find the volume stretching factor of the one parallelograms associated with that parameterization, you need to compute the square root of determinant d gamma transpose d gamma and integrate that over the parameter bounds that describe the manifold. And we'll be doing this a lot this week. A few refresher points is that our old rules for a parameterization of a manifold were pretty strict. We had to choose this nice open set in the parameter space and then find a parameterization gamma that mapped us from the parameter space onto the manifold, and it followed a couple of rules. One was that it was continuously differentiable. Look at how important that is now. Oh my God, we need to have these nice functions right here that will ultimately be integrated with respect to some parameter. So it needs to be continuously differentiable. There has to be a bijection, both one-to-one and onto, from the parameter space to the manifold. That means that every single point on the manifold gets hit. That's the onto part of that. And then the one-to-one part means that there is only one point in the parameter space that maps to a particular point on the manifold. And it has a derivative d gamma that is everywhere one-to-one. Its kernel is zero-dimensional. And these strict rules fail for important parameterizations like the one I just talked about, where we were talking about the unit circle or the unit sphere here. But note that these are actually okay because the problems are confined to a set of volume 0. Note that here, theta being equal to 0 and 2 pi maps us to the same point. And here we have an issue when phi is pi over 2 or negative pi over 2. We also have the theta 0 to 2 pi issue, 0 and 2 pi issue, I should say. And that's okay, because the problems are confined to a set of volume 0, which won't affect the value of a Riemann integral. So we can safely use these sort of relaxed parameterizations that are not quite one-to-one, or that have a derivative whose determinant may be 0 on a set of volume 0. As long as it's happening on a set of volume 0, we're all good. So I guess I kind of spoiled the surprise earlier, but the big deal about this is if we take a k-dimensional submanifold, the formula for its volume is the following, right? Here, we note that we have to parameterize the manifold, and what we want to do, here we would be integrating 1 over the manifold. Here, we find a way to describe the manifold using a parameterization. We compute the Jacobian of that parameterization, and that's going to give us the necessary k parallelograms that we need to use to approximate volume. Then we're going to find that volume stretching or scaling factor by taking the product of the d gamma transpose d gamma, taking the determinant of that, and taking the square root of that because we'd already proved at the very beginning of the lesson that this is going to be equal to the volume stretching or scaling factor, or the volume of the k parallelogram, I should say. And we want to integrate these tiny k parallelograms over the parameter bounds that adequately describe the manifold. Note that in the case where k equals n, note that the dimension of the manifold may not be the same as the dimension of the space. There's a difference between looking at a ball and saying what is its volume versus what is its surface area. With volume, you need 3 parallelograms. With surface area, you need 2 parallelograms. And those parameter bounds, there are more of them when you're dealing with volume than when you're asking about surface area. So in the event where the dimension of the manifold and the dimension of the space are the same, note that what ends up happening to d gamma is that it's square. And so the determinant of the original matrix d gamma is equal to the determinant of d gamma transpose. And so the determinant of d gamma transpose d gamma equals the determinant of d gamma times the determinant of d gamma transpose. And basically, what you end up having under the square root is the square of the determinant of d gamma. Right, this relationship is written out right here. And the formula actually just reduces to the familiar change of variables formula, because we've been using that, we used that last week. So in the instance where the volume, the dimension of the manifold you're trying to compute volume for, and the space are the same, this is just a regular change of variable. This is this new application really comes in handy when we're actually trying to compute maybe surface area, two-dimensional volume in three-dimensional space. And note that because of this square root under the integral sign, this formula tends to lead to integrals that cannot be evaluated using antiderivatives. We will be doing some where you can evaluate them, but more often than not, you end up with quite a mess here. Not to worry though, we won't be asking about those on quizzes and exams.